It's a great pleasure for me to be here today, and I thank the organizers for inviting me to give this talk. I also want to thank the European community for granting the initial training network called ZIP, is the acronym of Zooming in Between Plates, is a project that has been thought and coordinated by Philippe Agal from the nearby UPMC University. It is has been a good environment where this research I'm going to show you took the steps. I also want to thank the people who has been working together with me. Okay, there's not a full list, but we share the work, field work and microstructural analysis with Giorgio Pennacchioni, Mattia Agilio, and Luca Notini. We did the people who was doing the analysis, the high magnification SIM analysis has been Oliver Plumper and Michael Bestman. And Fabrizio Nestola is the one who worked with X-ray diffraction to analyze the glass and the crystal. So what I would like to show you today is a specific case study, not a big picture. It's a case study of a paleo earthquake that is witnessed by pseudotachylite, and Christina Dunkel did a wonderful explanation of how these rocks can form. They are essentially related to the frictional heating and melting of a rock along a moving fault plane during a seismic event. And the pseudotachylites here had been found inside a subducted slice of oceanic lithosphere that has been exhumed in the Alpine fossil subduction zone. So to give you an idea of this pseudotachylite, just to begin with, this cover image is the microscope view under cross polarizers of a pseudotachylite cutting a gabbro from this oceanic sequence. And you can see nice spherulites here, which are related to the fast cooling of the melt, growing crystals like needles of clinopyroxene and plagioclase grown together here, and they are setting in a matrix of glass. Most of this stuff here that is black is glass, and in my opinion, the preservation of glass here in these rocks is quite extraordinary, because if, as we think, the pseudotachylite and the seismic event occurred when the rock was sitting under Eclogite-Facies conditions at intermediate depth in the subduction zone, so the preservation of glass from 80 kilometers depth for such a long time, I mean 40 to 50 million years ago, it's important because it can tell us about the environmental conditions during development of the fault and of the seismic event, and also importantly about the presence or absence of water during this event, which is in turn important to understand the driving mechanism or driving possible mechanism for this earthquake to occur. So this is the scientific address of the talk. And I would like to start with that, telling that most of we know about the subduction zone seismicity arises from geophysics and from experimental and modeling studies. Here, for instance, are seismic tomographies of subduction zones showing that in between the converging plates, we can frequently detect a layer, this one that is several kilometers thick, of low velocity rocks, I mean low velocity of the S and P waves. And this because the rocks are hydrated or contain hydrous minerals and host pressurized pore fluids, which are the nest for the earthquake to occur here. And the earthquakes are also in the dry mantle of the downgoing subducting plate or in between it in the double seismic zones. And the most accredited mechanisms to explain these earthquake activities are, to my knowledge, are either the dehydration and brittlement here due to the presence of hydrous rocks or fluid activity. And here the most accredited mechanism is the thermal runaway, which is a mechanism that requires the co-seismic development of ductile deformation horizons, I mean shear zones or mylonite that localize the fault plane and let the earthquake go through the plate. And in this debate, very few is the information arising from natural rocks. We've seen examples from the continental crust, but the information is very few coming from field-based studies of high and ultra-high pressure rocks. And this because the seismic structures in these rocks are difficult to find, to read, to interpret, and importantly, to be preserved, as we will see. So for this reason, pseudotachylites are among the most reliable markers for an earthquake activity in a rock. And there are very few reports of pseudotachylite in subductions on rocks. Christina Dunkel has just shown you what happens in the subducted continental crust from Western Norway. Here I would like to mention the blue schistophyolites from Corsica, whose pseudotachylite form in a four-arc environment, so shallower than Eclogite-Facies conditions. And what we still miss is a clear example, or clear as far as I can show you now, of a pseudotachylite forming in a subducting oceanic lithosphere when it goes through Eclogite-Facies conditions at deeper intermediate depth. So this is why today I would like to show you the story of the Lanzo pseudotachylite. This is a field exposure of Lanzo peridotite, okay? And this is a pseudotachylite vein cutting through, and they can be as thick as 20 centimeters. And the peridotite and the gabbro, oceanic gabbro that is associated with it is quite fresh. This is a well-preserved mantle tectonite fabric made of oriented olivine, Clinopyroxene spinel. It is also containing plagioclase impregnation due to the flow during the mantle story of these rocks of melts, crystallizing plagioclase here, and it's pretty fresh. Although this peridotite underwent a subduction and exhumation story during the Alpine orogeny. And so there is a metastable rock, and this because the initial water content of this peridotite and the associated gabbro was so low that this prevented the kinetics of metamorphic mineral crystallization and also the ductile deformation to occur. But if we look at carefully inside these rocks, we can find the evidence that these earthquakes did occur when they were sitting under Eclogite-Facies conditions and going down metastably. For a large part of this peridotite body. So this is what I would like to show you. From a regional point of view, this peridotite and this ophioline massif is here west of the city of Torino. We are in the Western Alps. It's a high-pressure terrains and ophiolitic terrains exhumed here. And this is the massif, is a north-south elongated massif between the valleys of Lanzo and Susa, and this is the southernmost body that is called Moncuni, and this is the place the rocks I'm going to show you are coming from. So the body consists of a large core of pretty well-preserved mantle peridotite bound by serpentinized domains here and here. So this foliation here on a regional scale is a mantle tectonite foliation that the rock acquired during the mantle evolution, during rifting, and its exposure close to the ocean floor during opening of Jurassic Tethys. At that time, it was intruded by oceanic gabbros, 160 million years old, and then all of this oceanic lithosphere underwent interaction with ocean water that was heterogeneous. It mostly affected the serpentinized domain here and here, bound in the peridotite core, and also here, and only scarcely in terms of volumetric extent affected the core of the mantle peridotite and the associated oceanic gabbro, maximum 10% volume of the entire body. Then these rocks, this stuff underwent subduction and exhumation, and mostly the subduction zone deformation and recrystallization affected the wet domains, the serpentinites here and here, and the hydrated domains inside the strong peridotite body were crystallized statically into Eclogite-Facies assemblage, but only in a few places. So if we get a serpentinized peridotite, it shows a story from these domains here. It shows a story starting from low-grade serpentine that forms in these rocks under low temperature conditions during interaction with the ocean waters, and the story is pretty well shown by Baptiste Debray in his paper. Then during subduction, the chrysotile or lizardite are overgrown by higher temperature and pressure antigorite serpentine, and then at high pressure conditions, we have formations here of high pressure metamorphic olivine. I mean, 2.5 GPa and 550, 600 degrees. And at the same time, the associated gabbro transformed into eclogitic metagabbros, same time and conditions. So this is what we know from the literature. Let's have a look at inside this body, or particularly here in the Moncuni. This is a bad field sketch of this rock. I mean, this is the fresh peridotite, this is the gabbro dikes cutting through, and the gray domains are the minor hydrated domains affecting the peridotite and the gabbro. They are maximum 5% by volume, up to 10 probably, but very low amounts in terms of volume. So if we zoom in into this peridotite, it underwent metastabile whole the story. It still displays mantle tectonite foliation, and the pseudotachylite is cutting through. Inside the pseudotachylite, we can find large clusters of the rock-forming mantle olivine, which is quite uniform in composition, and it is setting in a matrix, this one of microliths, I mean crystals which were crystallizing from the fast cooling melt. And this is olivine, this is orthopyroxene, the light gray here is clinopyroxene, and these white shiny dots are spinels. So this assemblage, the pseudotachylite microlith assemblage, was crystallizing from the melt under relatively high pressure conditions because the spinel is stable in these aggregates. If we zoom in the gabbro, this fresh gabbro, it preserved plenty of the magmatic textures and of the magmatic minerals, and it also shows to record that mylonitic foliation developed under high temperature conditions when the rocks were still in the ocean, and this led to the elongation here along the mylonite fabrics of the pyroxene, the plagioclase, and the olivine, which are still pretty fresh from this stage, and everything here is cut by the pseudotachylite veins. You can see them here. If we zoom in into a hydrated gabbro, okay, we see it is undeformed, but actually this is not a gabbro, it's a metagabbro, because here the original magmatic minerals have been statically overprinted, we say pseudomorphosed, by high pressure minerals affecting the pyroxene, the plagioclase, and the olivine here. So this pseudomorphic replacement of the gabbro, you see, are dissected and by sets of microfolds, which also host tiny pseudotachylite liquid. So we see different story, preservation of the initial assemblages here when the gabbro is fresh, and recrystallization to high pressure conditions when the gabbro is hydrated. So it's due to kinetics, this. And importantly, what we learn from this is that during this subduction experience, this gabbro does not deform in a ductile fashion. The only ductile deformation we see predates subduction and is high temperature, either here in the ocean for the gabbro or in the mantle for the peridotite. We don't see ductile deformation during subduction, and the pseudotachylite are cutting through all rock types. So to me now it's important to understand what are the mineral transformations here, because it's important to find a setting for the pseudotachylite forming event. So this is the metagabbro. The plagioclase here is gone to jadeite and zoisite. The pyroxene has gone to omphacite, and the olivine, this one here, has gone to talc and tremolite during the high pressure Eclogite-Facies recrystallization, and there are coronas of garnet and chloritoid in between. If we take a hydrated domain, this guy here in the peridotite, it is different from the fresh mantle peridotite. You can see here a pseudotachylite vein cutting through, and the rock contains olivine, which is composite. I mean, a course of mantle olivine overgrown by light gray. Here is the metamorphic high pressure olivine, which is more or less stable with antigorite, and this kind of a fish here is a pseudomorphic replacement after the original mantle plagioclase that during subduction goes to a chlorite rind and garnet and zoisite core. So this is how the rocks look like when they recrystallize under high pressure conditions, and this is pretty common all over the high pressure metaophiolites in the Alps. Here we can see a contact between a high pressure eclogitic metagabbro, this one here, and this is high pressure serpentinized metaperidotite. And these are sets of pseudotachylite veins cutting through, and they are parallel to set of damaged microfolds into the host rocks that cut through the eclogitized plagioclase, and you see here dissect the clinopyroxene. And if we zoom in exactly into this clinopyroxene, we see it's brecciated with fragments of magmatic clinopyroxene set in a matrix of omphacite. So this implies that the breakup of this pyroxene, the rupture along this fault, took place during Eclogite-Facies conditions to form the omphacite here. And if we zoom now into this microfold here, we can see it is branching, it's cutting through a fine-grained recrystallized plagioclase site, and it contains a rod here that is made of coarse zoisite and jadeite, and is cut by tiny omphacite veins. You can see them here, 1, 2, 3, all these veins that are truncated by the microfold. You can see even here. And the microfold here is overgrown by this one that is high pressure, dendritic garnet. So this is an eclogite-Facies garnet, but has a dendritic form. So this implies that the microfault formation, the setting of the earthquake, is within a stage of eclogite-Facies recrystallization of the gabbro. If we look inside the high-pressure serpentinized metaperidotite, we see the same. Pseudotachylite cutting through prograde antigorite veins. And if we look at the the olivine clast inside the pseudotachylite veins, we can see here they are composite again, and they display a mantle olivine core overgrown by high-pressure metamorphic olivine. And if we pick up a vein like this, a pseudotachylite vein, we can see here, it contains clast of OPX and olivine truncated by antigorite veins, which are in turn truncated by the pseudotachylite melt. And this inside, embedded in the pseudotachylite, is pseudomorphic replacement after the mantle plagioclase. We can zoom here. This is the boundary of the pseudotachylite vein. This is the host rock. And this is the pseudomorphic replacement, after plagioclase, mantle plagioclase. You can see here the chlorite rind, the garnet, and the zoisite are dismembered into the pseudotachylite melt. So this implies, again, to get this, we should have a rock that is already eclogitized when the pseudotachylites are cutting through. So this, again, is an indication that the event was at intermediate depth. And I don't know if you see it, but there's a vein that is cutting through the metagabbro into the metaperidotite, and it's also cut the pseudotachylite vein. I show you a close-up, of this vein. You can see it here. And when it is inside the metagabbro and the high-pressure recrystallized plagioclase, you can see the vein contains zoisite, omphacite, and a bit of chloride, so a high-pressure vein assemblage. When it cuts through the ultramafic part of the sample, it is containing talc and tremolite, which is exactly what we find on top of the magmatic olivine. So this is truly a high-pressure vein that cuts through the pseudotachylite, and this seals this subduction earthquake event under eclogite-Facies conditions. So it is quite important, to my point of view, to look at this minor hydrated volume, because they do recrystallize under high-pressure conditions, and the relationships between high-pressure minerals and the pseudotachylite structures is crucial to define the setting of the earthquake event. Okay, this is much more difficult to do when we deal with a fresh gabbro. They can contain, you see, a very thick, centimeter-thick black pseudotachylite veins like this. And, but in this case, the absence of water inhibits the crystallization of high-pressure mineral markers. So unless we find a sample like this, it's difficult to test if the pseudotachylites are indeed subduction related. So this is a cataclastic gabbro. This is a scanning electron microscope view, and it's pretty fresh in terms of magmatic mineral. This is magmatic clinopyroxene, olivine, and plagioclase, and you see it's cut by sets of pseudotachylite veins, and this is a fault vein, and this is an injection vein, and they contain here pure glass, and in some cases, in this part here, glass plus microliths, which are crystallized quickly, fastly, from the fast cooling melt. So we have dendritic clinopyroxene that is different from the magmatic one. We have microliths of plagioclase and garnet with eclogitic composition sitting in the glass, more or less here. And this is a microcrack that is related to the fast cooling of the melt that cracks. And the crack is decorated by eclogitic garnet microliths, and this is a pseudotachylite from a nearby rock, a mantle pyroxenite, and you can see inside this pseudotachylite we can find eclogitic dendritic garnet that grew very fastly from the fast cooling melt. So we can have garnet here, luckily precipitated by the pseudotachylite melt when it cools. But we can also find in the surrounding rock garnet, metamorphic garnet, that is a corona between the fresh olivine and the plagioclase, but we find this metamorphic garnet just here, not elsewhere in the rock, and this is probably due to the heat released by the pseudotachylite that enhances the kinetic of metamorphic garnet growth here. So we have a nice correspondence between eclogitic garnet crystallization, either in the rock or in the pseudotachylite vein, that is a further indication that the earthquake occurred under Eclogite-Facies conditions. So we can try to use these samples in order to achieve some information that could be relevant to those of you who work on the mechanical behavior and the formation of these earthquakes in subduction zones. For instance, we can test how much water is in the glass. If the glass is dry or not, this is glass crystallized in the tiny garnet, and this is a beautiful chain olivine sitting in the glass. So this is related to the very fast cooling. And if we analyze the glass by Raman spectroscopy, we see no peak in the OH stretching region. So the glass is fully dry. And this implies that there was no water available during the seismic failure in this rock, so the environment was really dry. So now, so this seems to be ruling out a role of a fluid phase in breaking up these rocks. And we can also test the style of the formation in the rocks surrounding the fault in order to see whether we can find some ductile deformation localizing the fault plane. So this is the example, the sample, the picture I showed you before. It is sitting here in the larger scale sample. This is another picture taken at cross polarizers under the microscope. And you can see this is the fault plane. It dissects the pyroxenes. And the black stuff here is the glassy pseudotachylite melt. These are the injection veins. And you see the rock is fully cataclastic, but we can find here, in between the broken pyroxene, some recrystallization domains. So we are doing, this is recent analysis, ABSD profiles along it, and we can see the coarse pyroxene is dissected, but the misorientation is not big. Even here, we are down here in this part, and this is the recrystallization domain. Or the is not a recrystallization, it's a cataclastic rupture, because we can see here the pyroxene grain do not display any preferred orientation. This is also shown by the stereo plot. This maxima refer to the continuous measuring of this coarser pyroxene class, but actually there is no preferred orientation. All of this seems to be cataclastic. So this seems to rule out the importance of ductile deformation to localize the fault plane. I mean, it's full cataclastic. And, but this is important because if we, I would like to come back to the discussion done by Christina Dunkel. This earthquake ruptures create a strong cataclastic damage zones around them. They could be really thick and depends on the density of the pseudotachylite vein. Here, for instance, we have a view of this area from an optical microscope, and we can see the grain size of the initial gabbro is strongly reduced, and this strongly increases the permeability. So this rock is a sponge, is a channel way for fluid flow, but if we look at the mineralogy here, we find mostly unstable or metastable magmatic clinopyroxene, magmatic plagioclase. This is olivine without any transformation. So this means that this rock was not invaded by a fluid, was not recording any fluid flow, because otherwise it would readily transform into either an eclogite or a blue schist or a green schist, depending when it meets the water. So here again confirms that the rock is fully dry during, before, during, and after the earthquake development. So it's a nice metastable stuff going down. And this has been also shown in Western Norway. So I go back to the presentation of Christina Dunkel, where they have recently found that the former old granulitic foliation here is a billion years old, I think, is cut by these fault planes which are related to the Caledonian subduction of this slab of continental crust. And inside this, you can find pseudotachylite. So this actually a fault really related to an earthquake, and this changes the permeability of this stuff here. The water answer enters, wet the rocks, and these ductile shear zones are developed. These are well known since the late 80s by the work of Håkon Austrheim, and these are the ductile shear zones developing a hydrous Eclogite-Facies assemblage with amphibole, with epidote, with fengite, that indicates the flow of fluid and of channelized ductile deformation here, and this leads to formation of large-scale deformation zones which structure the downgoing continental crust during subduction, and these are the pseudotachylite findings that could be the precursors for these large ductile shear zones developed under Eclogite-Facies condition to develop. So what happened in the continental crust may happen also and may explain many things related to the deformation of the oceanic lithosphere during subduction. So to summarize, this example I showed you is quite different from many alpine high-pressure ophiolites, which are much more hydrated, much more serpentinized, for instance. The eclogite recrystallize on and on during subduction and deform on, and all the associated terrain, because they spend most of their subduction lifetime within this low-velocity zone or plate interface, which is very rich in fluid and a site for fluid activity. Instead, Lanzo, in my opinion, is coming from the dry mantle of the downgoing subducting plate, and it might be, probably, I don't know, a good proxy of what may happen here in the double seismic zone in terms of rock behavior. And to summarize this, Lanzo and Moncuni lithosphere, oceanic lithosphere during subduction are fluid-free, metastable, dry, strong, stiff. They are big resistors in the subduction environment, subduction zone environment, so they can, in principle, accumulate large differential stresses. And the pseudotachylite that I showed you, to me, is a good marker of an earthquake that occurs under intermediate depth. So they could be a kind of a proxy of what happens today in the dry mantle of the presently subducting Pacific oceanic plates. Going back to this example, we can rule out or we can doubt that the dehydration and brittlement or the thermal runaway were the mechanism to unchain this earthquake activity. So as an alternative hypothesis, I can propose or suggest or imagine the slab unbending that has been proposed by Emanuele Faccenda that releases here in this gray region where the rocks undergo eclogitization like Lanzo, a deal of seismic energy. Or I would like to go back to the presentation of yesterday by Nadège Hilaret. She showed the experimental work of Thomas Ferrand. What happens? So what I was saying, this experiment, this is the starting material used by Thomas Ferrand in his experiment, and he chose a starting material with a few antigorite, 5% by volume, and this is similar to what we observed, for instance, in the distribution of hydrated domains within the dry Lanzo peridotite or oceanic lithosphere. So more or less they're the same proportions or comparable. And what Thomas said, Thomas tried to relate the hydration of antigorite to the seismic behavior of his samples. And he did a nice job to do that, in my opinion, because he said that during the hydration of antigorite, there's a volume change, and this led to the collapse of this serpentinized domain. And what is transferred from these serpentine domains to the rigid olivine asperities is the stress. Is the stress that percolates to the olivine blocks and lead them to quake, and also in his experiment to develop a tiny bit of let's kind of a pseudotachylite liquid. So the results of Thomas, although on a small scale, look similar to what we observe, for instance, in Lanzo, but we still have to work a lot in order to come to these conclusions. Is just an idea. So in the next years, I hope to be so lucky to continue to work on these rocks. And so I thank you very much for your attention. This is nothing to see with Lanzo, it's the Monviso. I know that Philippe is happy to look at the Lanzo, no, Monviso, sorry. It's over.